Hello, Team GChem, and welcome to today's lecture, where today we're going to be talking about two really important concepts in general chemistry, molar mass and the concept of the mole. And so by the end of today's lecture video, I'm hoping that you'll be able to calculate the molar mass of any chemical compound, and that you'll be able to convert between units of mass in grams, moles, and the number of atoms or molecules that can be found in a given substance. I've taken a lot of today's lecture from our OpenStax textbook, section 3.1, so after watching this video, if you'd like a little bit more information or a different perspective, I encourage you to check that out. And with that, let's go ahead and get started. So molar mass is a concept in general chemistry that tells us exactly how much a molecule weighs. And the nice thing about it is that you can calculate the molar mass of a compound using only information found on your periodic table. Now, I'll let you know before we get started that depending on what textbook you're using or what video you're watching, you may hear a lot of synonyms for this phrase molar mass. So if you hear molecular mass, molecular weight, formula mass, or if you see some of these abbreviations like MW, or FM, it all means the same thing. We're talking about the same concept. You'll just see it in slightly different contexts. How we calculate the molar mass is that we are going to sum up the average atomic masses found on our periodic table for all the atoms represented in a substance's formula. And I think this is best demonstrated by an example, so let's go ahead and dive into one such example. Here's chloroform. Fun fact, it's used was used historically in a lot of local anesthetics. It's one of the precursor molecules that we need to make our Teflon and our nonstick pans at home. And we know its chemical formula is CHCl3. And so if we want to come up with the molar mass for this compound, we're going to sum up all of the average atomic masses. And so I've shown that in this little figure here, but let me just really hammer home that where I'm getting these numbers from, this 12.01, 1.008, and 35.45, is all coming from our periodic table. So if I zoom in here on our periodic table, you'll see that the number reported for the average atomic mass of hydrogen is 1.008. For carbon, element 6, it's 12.01. And for chlorine, it's 35.45. And so all of these are the numbers that we're going to end up using when we have our average atomic masses. And so one way we can do this is we can say that, well, if there's one carbon, one hydrogen, and 3 chlorines, then I need to add together the numbers 12, 1.008, and actually 3 times 35.45 because I have 1, 2, 3 chlorines present. So if you like, you can do that and generate your little subtotals for each of the different elements that are present, add those all up together, and we're going to get a molecular mass of 119.37. I sometimes like to do this all in one line, and that is totally fine. So if I was doing this on my piece of scratch paper to determine the molar mass, I may say that there's 1 times 12.01 plus 1 times 1.008 plus 3 times 35.45, and that'll give me the same number. So again, we're just adding up for each atom that is present in the compound all of our average atomic masses, and that's going to give us our molecular mass. Let's go ahead and do a second example, this time with aspirin. And for this, I'd actually like you to pause the lecture video at this point and see if you can calculate this molecular mass on your own using the periodic table that you're able to pull up online. Once you've done that, or at least given it a good attempt, then go ahead and unpause the video and I'll go through the solution. Okay, so for aspirin, we need to know the average atomic masses for 3 elements, carbon, hydrogen, and oxygen. And so from our previous example, we already had 2 of these written down. So we've got carbon with an average atomic mass of 12.01, hydrogen 1.008, and then we'll need to look at our periodic table one more time and see that oxygen is 15.999. And so once again, if we're adding up all the atoms and summing it to get our molecular weight, the easiest way to do that is to say that there are 9 carbons, each with a weight of 12.01, plus 8 hydrogens, each with a weight of 1.008, plus 4 oxygens, each with a weight of 15.999. When I add that all together, I'm going to get a molecular weight of 180.15. Now, something you may have noticed is that despite the fact that I'm always going on and on about class, about units in order to make sure we've done things, so far I haven't talked at all about what units we should be using to describe our molar weights. And that's in part because there's actually 2 right answers for what the units should be for our molecular masses. And they're equivalent. So the numbers that I've given above works if you're talking about these masses in terms of units of what's called atomic mass units, or AMU, or if we're talking about grams per mole. And so in this previous example with aspirin, it would be totally appropriate for us to say that the molar mass, or the molecular mass, of aspirin is 180.15 AMU. And I'm not going to dwell on this unit too much, because while this tells us the weight of one molecule of aspirin, it's not used too much in our general chemistry course. We're going to be much more concerned with dealing with units of grams per mole. And once again, the number is the same, but the unit is different. And so this is also equivalent to 180.15 grams per mole. And that's great, and that grams should be a very familiar unit to us at this point, but I've probably raised more questions than I've addressed, because, well, what is a mole? And I've posted one link in the video description that if you want to know more after watching this video about what a mole is, if it doesn't feel quite intuitive, I encourage you to watch it. But I'll go through briefly both the concept of a mole as well as the numbers that are associated with it. So a mole is Latin for something meaning bulk or large mass. It's essentially a chemist's way of saying that if we have a collection of particles that we can see with the naked eye, how many atoms or how many molecules are there? And I'll use the word particles to be general, but again, particles could be atoms or molecules, depending on the context. In fact, moles, you could even talk about a mole of umbrellas or a mole of eggs. So it's not a word that has any defined context until we give it one. And there, as chemists, most of the time we're going to be talking about atoms or molecules. This is the same connotation for kind of dealing with collection words like you might be more familiar with in English, like the word dozen or trio or pair. So for example, if I have 1 dozen eggs, you know that I'm talking about 12 eggs. And if I have 4 pairs of students in class, well, you know that a pair is equal to 2, and so we have 4 times 2 equals 8 students total. So when we deal with moles, a mole is just going to refer to a certain number of particles. And we can also talk about 2 moles of a substance, or 3 moles of a substance, or 7.4 moles of a substance. And then we just need to multiply in order to get to the total number of atoms or molecules that are present. So what is that conversion factor? A mole is equal to an Avogadro's number of particles, specifically 6.022 times 10 to the 23. And this is going to be a conversion factor that allows us to convert between units of moles and the number of particles, such as atoms or molecules. If you want to know a little bit more about why it's this specific number, like 6.022 times 10 to the 23, why? It actually relies on this answer above, where chemists, when we were coming up with what the concept of a mole was, we didn't want to have to change the number for the molecular mass, whether we were talking in AMU or in grams per mole. And it turns out the only way we could make that happen was to make the mole, an Avogadro's number, be this very specific quantity. So always, this is our number. It's kind of just something to know or to memorize or to have given to you on a test. In our class, we'll have it given to you on the test. But it's our conversion factor, and we can use it just like we did in chapter 1 anytime we want to convert between moles and number of particles. So with this information, both about our relationship between molecular mass and moles and our relationship between moles and number of particles, let's go ahead and do a couple of practice examples with one another so that we can use all of these concepts in order to learn quantitative information about our atoms and molecules. And so again, if you feel like you might know how to do one or more of these examples, I encourage you to pause the lecture video and try them out on your own first, or you can watch me go through them one at a time. Okay, so first example, how many moles are present in 5 grams of chloroform? So this reads a little bit like a chapter 1 problem, and indeed, in some ways, this is just like a unit conversion. And so what we're going to want to do for this problem is we are going to want to find a conversion factor that allows us to translate between grams and moles. And you may notice since chloroform, CHCl3, was one of our examples earlier for calculating the molar mass, that we actually have that conversion factor. We know that there is 119.37 grams per mole of this chloroform. And so we can write that in a variety of ways. I'm going to choose to write that for the purposes of this problem as 119.37 grams of chloroform is equal to 1 mole of chloroform. And so compared to chapter 1, we're now going to use the exact same strategies that we did before. I think the only thing that's really new knowledge in this chapter is that because each molecule has its own unique conversion factor, its own unique molecular weight, we always need to look at the periodic table every time we're dealing with a new substance in order to find out what is its unique molecular weight. Okay, so trying to do a grams to mole conversion, I'm going to go ahead and set up my little railroad tracks here. I know the starting quantity that I'm going with is this 5 grams, and I would encourage you to always put the molecule that you're talking about in the problem, because once we start dealing with chemical reactions, we're going to have lots of different molecules showing up in our word problem, and it's always good to keep track of which specific molecule we're doing a conversion on. So here, we're trying to convert chloroform to those units. Currently, I've got grams up top, so I'm going to want to put grams in the bottom. And moles up top in order to get my units to cancel and to be left in units of moles. I'll do a quick double check, see that my grams of chloroform is canceling out. I'm left in units of moles of chloroform. And so in order to get my final answer, I just need to plug these numbers into my calculator, 5 divided by 119.37, and I'm going to get, again, out of my calculator, 0.41886 moles of CHCl3, which then I'm going to try and use the appropriate number of sig figs to report my final answer. Our molecular weights are termed exact quantities, so they don't factor into how many sig figs we report in the final answer. And so here I'm just using this 5.00 with 3 sig figs, and so I'll go ahead and report my answer to 3 sig figs as well, which would be rounded to 0.0419 moles of chloroform. All right. Good work on that problem, and let's go ahead and move on to a slightly different problem. Here, we're going to be asked to calculate how many atoms of copper are present in a 5-gram sample of copper wire. So once again, we're going to need to be able to determine what are appropriate conversion factors for this problem, and let's start by calculating the molar mass of copper. Copper is just Cu. And so we can look up that number on our periodic table. And 1 copper means that we can just go ahead and write down this number that we see from our periodic table as the molar mass. So we've got a conversion factor of 63.546 grams of copper is equivalent to 1 mole. Now, that will help me get from grams to moles, but the problem asks me to solve for something in terms of number of atoms. So this is now starting to look to me like a two-step unit conversion process. I don't have anything from my periodic table that directly tells me grams to number of atoms. However, here's where Avogadro's number is going to come in handy. This 1 mole being equivalent to an Avogadro number of particles also applies to our copper sample. So we also have a unit conversion that tells us that 1 mole of copper is equal to 6.022 times 10 to the 23rd atoms of copper. Here, I could say particles of copper instead. I don't want to say molecules because copper is just like a single atom. So here, that's why I'm using the word atoms when I'm talking about Avogadro's number. Okay, so now we have 2 conversion factors, and let's see if that's enough for us to do this conversion between grams and number of atoms. One more time, I'm going to set up my railroad tracks. The quantity that I'm starting off with is once again 5 grams. Here we're talking about 5 grams of copper. First step is to convert from grams to moles. And so I'm going to plug in my molar mass of copper on the bottom, 1 mole of copper up top. And that's going to help make sure that I cancel out my units of grams. But again, currently I'm in units of moles, and I'd really like to be in units of atoms. And so we're going to do a second step to our unit conversion. That's going to put moles on the bottom, again, so that units of moles will cancel, and number of atoms up on top. So you can see here that in order to get my units to work, it looks like I needed to multiply by Avogadro's number. All right. The second step allowed me to cancel out my units of moles of copper and to be left in the unit system that I wanted, atoms of copper. So going and plugging this information in my calculator, 5 divided by 63.546 times 6.022 times 10 to the 23rd is going to give me a final answer, once I round it to 3 sig figs, of 4.74 times 10 to the 22nd atoms of copper. Okay, so now we've seen 2 examples, both of doing grams to moles conversions and doing grams to moles to number of atoms types conversions. And so I'd like to leave us with one last example for today, a challenge problem if you like, that's going to ask us how many oxygen atoms are present in 8.37 grams of aluminum sulfite. If you can do this problem, you can basically do any problem that's related to molar mass and the concept of the mole. And so I'd like you to, again, pause the video at this point and see if you can come up with a solution or a partial solution to this problem. And once you think you either have the right answer or you're feeling a little bit stuck, then go ahead and unpause the video and I'll walk us through it. Okay, so this is kind of a multi-step problem where I'm missing a lot of information before I can set up my unit conversion. And maybe where I want to start is that for aluminum sulfite, I can't calculate the molar mass of this based on the name alone. I need to use my chapter 2 knowledge in order to go from a name to a formula. And so because we've got aluminum sulfite, this ionic compound, I know that I'm going to want to come up with a partial formula for the cation, for the anion, and then use something like the crisscross method in order to come up with what the overall compound's formula is going to look like. So we've got aluminum. Aluminum is element 13 on the periodic table, and you may remember that these elements in group 13, when they're part of compounds, always have a 3+ charge. So let's go ahead and write that down, Al3+. Sulfite is one of our oxo anions, and its formula is SO3 2-. Once we do the crisscross method, that's going to tell us that we're going to want to have 2 units of aluminum and 3 units of sulfite. So our formula for aluminum sulfite is Al2SO3 3. Okay, So now that we have a formula, we can go ahead and determine the molecular mass of this compound. However, this is a good example of where we need to take into account how parentheses influence how many atoms there are of each type. In particular, there's no parentheses around the aluminum, so we know that there are 2 units of aluminum. And looking at our periodic table for aluminum, we see that aluminum's average atomic mass is 26.98. So we can go ahead and write that information down as well. 982. Okay. And if we multiply these two together, this will give us our subtotal for aluminum, which ends up being 53.96 once you type it into your calculator. How about sulfur? You might think that there's only 1 atom of sulfur present in this compound, but actually this 3 works distributively. So we actually have 3 units of our sulfur, and from our periodic table, sulfur is element 16. And so this means that we have 3 atoms of sulfur, each with an atomic mass of 32.06. And that gives us a subtotal for sulfur of 96.1. Last but not least, for oxygen, again, this 3 applies distributively, and just like you would do in your math class, we're going to multiply the 2 numbers together. So we have 3 times 3 equals 9 atoms total of oxygen. And like we saw earlier in the lecture video, each oxygen has a molecular or an atomic mass of 15.999. So putting all that information together and coming up with our various subtotals and then adding them together, or if you like, you can do this all in one line, we get a grand total molar mass for aluminum sulfite of 294.14. Phew. So this finally tells us what should be our conversion factor to get from grams of aluminum sulfite to moles. Okay, so let's go ahead and write some of these conversion factors down just for our reference. We've got 294.14 grams of aluminum sulfite being equivalent to 1 mole. And then once again, we know Avogadro's number is going to work for us. So as soon as I have moles of aluminum sulfite, we know that that's going to be equal to an Avogadro's number of particles. And here, I'm going to use the word molecules because I think that's the word that makes the most sense, since aluminum sulfite is a molecule, not an atom. Okay, so let's go ahead and start off our railroad tracks. I know my starting unit is 8.37 grams of aluminum sulfite. And I know what my molecular weight is, and so I can once again put grams in the bottom. And moles up top. Now I'm obviously not done yet because my problem is asking me for a number of oxygen atoms. And so I'm going to again need to do a multi-step unit conversion process. And I'm going to, in order to get my units to cancel appropriately, put in my second information for my second conversion factor, which tells me that 1 mole of aluminum sulfite is equivalent to 6.022 times 10 to the 23rd particles. Okay, let's do a quick unit check. Gotten rid of grams of aluminum sulfite, gotten rid of moles of aluminum sulfite, but currently my units are actually molecules of aluminum sulfite, and I'm asked about oxygen atoms. So I'm going to have to come up with one more conversion factor in order to get to my desired unit system. And I can do that. Turns out a third place to get conversion factors from is just looking at the chemical formula itself. And so here, I notice when we were calculating our molecular weight that for every 1 molecule of aluminum sulfite, I had 9 atoms of oxygen. Again, we got that conversion factor, not from our periodic table, not from some universal constant, but by taking a really close look at the chemical formula itself. And so we can use that conversion factor as the final step in our process in order to get to the right unit system for this problem. And now, taking a look at our units, molecules of aluminum sulfite cancel out. Our current units are atoms of oxygen, which is exactly what we wanted. So we're ready to pull out our calculator, multiply, and report our answer to 3 significant figures. And once you do this, we get an answer of 1.54 times 10 to the 23rd atoms of oxygen. All right, so again, this was meant to be a hard problem, but if you can learn to be comfortable with the 3 ways of getting unit conversions that we practiced, you'll be well on your way to being able to solve any problem that gets thrown at you. So let's wrap up for today with a quick summary. Hopefully what you've seen in today's lecture is that a compound's molar mass is determined from the periodic table. It tells us how much a molecule weighs, but perhaps more importantly, it allows us to be able to convert between various unit systems that chemists use frequently: mass, moles, and the number of molecules. Doing mass to mole conversions always requires us to use our periodic table to determine a compound's molecular weight and use that as a unit conversion factor. Going from moles to the number of particles just requires us to remember Avogadro's number and that there's 6.022 times 10 to the 23rd particles per mole of a substance. All right, that's all I've got for us for today. Thanks for watching, and I will hope to see you all in class come this week. Take care.